Okay, so we're recording. Last time we were talking about graphs and level sets. Both of these are constructions to help us draw pictures, to help us understand functions. But we draw different pictures that help us understand functions in different ways. And both of them are actually really valuable for doing multivariable calculus. Because they both are pictures that help us understand a given same function, it's not terribly surprising that they might have something in common with each other. Now, they are very, very different, but they do have something in common. And it's as follows. Notice that if I have a function from R2 to R1, I can talk about a level set by setting that function equal to a constant. Right? There's a level set of our function f. I can talk about a graph. Now, again, you've got to be careful. A graph is what happens when you set the function equal to a new variable. And while we're here, let me emphasize, look how different these equations look. I mean, kind of similar in a way, right? But this equation on the left has 3 variables in it. Right? This equation on the right only has 2 variables in it. These are importantly, significantly different equations. So here's the key idea. If you take a horizontal cross-section, keeping in mind that a horizontal cross-section says you're slicing like this, right, totally horizontally, it means you're just setting z equal to some constant, thus that equation. When you take a horizontal cross-section of your graph, well, look at what you have then. You've got f equal to z, and then z equal to c. Altogether, you have morally the same thing as f equals c. So the nice punchline here is that level sets are horizontal cross sections of graphs, and that's a nice pithy little conclusion. Level sets are horizontal cross sections of graphs. Something to keep in mind. I'm going to show you an example here. Here is an explicit function. We're going to look at x squared plus y squared. And let's see here. Step 1, let's look at a level set of it. A level set, again, what you get when you set the function equal to a constant. Of course, this gives you a bunch of circles. In this particular case, like so. Now let's look at the graph. We know how to do the algebra of this. You set the function equal to a new variable, in this case z. What we don't yet know how to do, but we will very, very soon, we don't technically at this point know how to figure out what this actually looks like three-dimensionally. And we're going to do that in like a couple of minutes. But for the moment, let me just assert that what you get here is kind of a bowl shape, so like that. So, and again, let's pause before I go on and notice how different these pictures are. Right? Not only are the equations importantly different, but the pictures are really dramatically different. This one is a surface that lives in space. This one is a bunch of curves in the plane, and they're unavoidably very, very different. Right? But again, you can see the connection between them by looking at the horizontal cross sections, and in particular, horizontal cross sections again are what you get when you set z equal to various constants. And notice when you do that, right? When you slice through this bowl, geometrically speaking, when you set this z equal to c, thus resulting in x squared plus y squared equals c, algebraically the same as the level sets, notice these slices are, in fact, the exact same circles that we were looking at there. Everybody happy? Okay, so neat fact. Now, a minor quibble. This is a minor. Let's not get super uptight about this. Technically, these aren't quite the same because, after all, these circles live in 2 dimensions, They consist of a bunch of points that have 2 coordinates, right? These circles live in 3 dimensions. They consist of a bunch of points that have 3 coordinates. Right, okay, fine, but nevertheless, you know what I mean. In other words, if you were to take any one of these circles, ignore the z coordinate, look only at the x and y coordinates, it would be exactly one of these circles. Okay. All right. Okay, moving along. So I think I've already expounded somewhat on this point right here. You got to be really careful with terminology and language and how you phrase things at this point, because it really matters. It makes a huge difference. You can't say graph when you mean picture, because some pictures are level sets. They're not graphs, right? And you can't say graph when you mean function, because a function's an algebraic object. A graph is a geometric object. Function's an algebraic object. So all these distinctions are important, and you got to be ultra careful. And the problem is, I recognize that when you're in a single variable calculus class, a lot of y'all probably took it in high school. They sweep all of this under the rug. They don't care, because practically every picture you draw in the Calc 1 class is a graph. So they let you get away with all sorts of sloppinesses because they don't matter in that class, but they do matter in a multivariable calculus class. And I've seen so many students kind of, sweep all this under the rug. Come on, what's the big deal? And then they get to a certain point in the calculation at some future time, and mysteriously, magically, they keep taking wrong turns. They don't know why they're taking wrong turns. They're just getting wrong answers over and over and over again. And the reason why is because they're not being careful with the language. It's really important. Okay, so just to as a yet another example of this, let's look at this example here. Got a line given, this line called L, and here's the equation, just so we have an algebraic foot in the door. And this is, of course, a geometric object. I'd like to understand some of the geometric features. I'd like to do some calculus, if possible, to help me understand this shape. To what function should I apply the calculus? Well, in fact, we're going to find that there's what I'm going to call a calculus of graphs. Namely, there is a way to relate certain kinds of derivatives to certain kinds of geometric interpretations on a graph picture. There is also going to be a calculus of level sets, which means that certain kinds of derivatives of multivariable functions will have certain geometric interpretations on a level set picture. You're going to have different geometric interpretations in these different pictures. So again, you got to keep it straight. So depending on which kind of calculus I want to use, if I want to use the calculus of graphs, to what function should I apply the calculus of graphs to help me understand this line? Well, I need to find what function, when I make the graph of it, will give me that line. So I'm going to try to reverse engineer then. Instead of a function being given and I try to figure out what the graph looks like, I'm going to say, let's pretend that this is a graph. Let's try to figure out what the function is. Right? And here's what I claim is the answer. I claim that this function right here is the answer. Now let me try to persuade you of this. Keep in mind, my assertion is that if I take the graph of this function, I'll get that line. Let's be careful and do it. We're going to take now the graph. Keep in mind what a graph is. A graph says I'm going to set the value of the function equal to a new variable. I'm going to choose y just for alphabetical reasons. This is what it means to take a graph. Right? Graph of a function says take the value of the function, set it equal to a new variable. And I claim that I win. I claim that this graph is this line. It doesn't look like it, but it's not too hard to persuade yourself that these two pieces of algebra are actually equivalent. So any any x and y satisfying this purple equation will also satisfy this green equation, and vice versa. In other words, you can do trivial algebra to get back and forth between these two equations. Is that cool? I'll leave the details of that algebra, high school algebra. Y'all can do that. Okay, how we doing? Now, I pulled this function out of a hat, right? A legitimate complaint here. How would I find this function in the first place had it not been just given in the statement of the example? And notice that in order to interpret this as a graph, I need y equals on the right. This is just trivial algebra right here. So how are you going to take algebra where you don't have y equals and manipulate it around to get algebra where you do have y equals? Y'all know how to do that. You solve the y, right? That's all it is. So the process of taking an arbitrary equation and rewriting it as a graph of a function is just solving for, in this case, y, and technically you could solve for either variable, and technically it's still a graph in either sense. Everybody good? All right. Okay, so next. Suppose I wanted, for whatever reason, to understand this line by using the calculus of level sets. And again, I know we don't know what that is yet, but we'll get to that not that far in the future. Hypothetically, if I wanted to use the calculus of level sets, I need this line to be a level set of something. What function is it for which a level set would give me that line? And I claim that this function does it. Now, again, I have to persuade you that this is the case. So let's actually take a level set of this function. A level set of this function is what you get when you set the output value equal to a constant, and I can, there's a bunch of different level sets. I only need to show that one of the level sets is my original line. That means I get to put anything I want here, and I'm going to choose 6. You probably saw that coming. And as promised, having taken a level set of this function, I get an equation that is equivalent to the original equation. So this line is a level set of this function called g. Yeah.
You were talking about being able to put any constant there instead of 6.
Yeah.
How would those different lines be related? So equal 6.
Yeah, I would say that they're all different level sets of this function. Now, those other level sets are not going to be equal to this line, and they're totally different lines. But this function g, for which one of the level sets is this line, that function g has other level sets, and they'd just be other lines about like that. Yeah. But technically irrelevant to the question as asked. Yeah. Everybody happy? All right. Now, before we go on, I want to real quick. Yeah.
Do level sets not have constants then?
Do level sets what now?
Not have constants?
I don't know what you mean. Have constants.
I'm sorry.
You're referring to the level set or to the function? Whose
function.
level? Yeah. So the function. There's a bunch of different ways that I can write a function for which one of the level sets is the line. So if I could, for example, how about if I were to make whoa, I didn't mean to. Sorry, I wanted to be in pencil mode. But if I were to say minus 6. Now, this is a perfectly reasonable function, and one of its level sets is the same line. It's a different level set. It's the level set I get where I set this equal to 0 in this case. But again, notice a level set of that function is, again, an equivalent equation. Is that cool? Yeah. So where you put the constant and whether you whip it over to the other side or if you leave it there and call that C, it doesn't really matter. I could move 3 of it over to there and leave 3 to be the constant. It's all good. Doesn't matter. Okay. So before we go on to the third part of this example, let me just point out that as promised, this function whose graph is our line, and this function, one of whose level sets is this line, look how different the functions are. Totally different functions. Right? This first function f only has one input variable. This second function g has two input variables. It's a function defined on R2. Right? They're totally different formulas. They're very different functions. So again, if you apply the calculus of graphs to this function right here, you're going to get a catastrophically wrong answer, or whatever that question might be. And likewise, if you try to apply the calculus of level sets to this function, crash and burn nonsense. Yeah.
So like the graph of like 2 would be like you set it equal to z.
Oh, okay. Now, okay, I hear where you're coming from. You could talk about the graph of this g, but that would have nothing to do with the original question. Yeah. Does that make sense?
Yeah.
Okay, yeah. Right. Is that what you were going to ask?
Yeah.
Yeah. Yeah.
So like it just like you could set it equal to a variable. It would just be a whole different.
Yeah, it's just a completely different thing. Yeah, that's right. So another thing you got to be careful about with these kinds of questions is don't forget to read the words in the question. Right. So I do have that happen sometimes where students will look at find a function for which one of the level sets is the graph of the following function. And students heard the word graph, and they heard the word level set, and they heard the word function, and they put them together in some other order, kind of like you were describing, and yeah, you get unrelated nonsense. Yeah. So very careful. Last observation I make before I go on. Notice that the algebra in this example is trivial. Right? It's middle school level pre-algebra. Nothing happened to speak of algebraically. Right? So what is important with all of this is not whether you did some algebra that relates to a valid answer. That's because that algebra is trivial. That's not what we're here for. Right? What's important about these questions, and by the way, you'll notice if you look through my old midterm exams, questions of this general category, this kind of sort, there's a bunch of them. Right? I've done this a bunch of times. I'm sure I'll do it again in the future. I have no promises, but it's not about whether you can solve for y. Right? It's about whether you interpret the question correctly, making valid interpretations of the words in the statement of the question, and whether you then use the words correctly, appropriately, strictly speaking, in the work that you produce. Right? And this is awkward and weird because, again, in high school, they let us get away with murder on this kind of thing. And so you have probably not only not trained yourself to use these words carefully, you've probably trained yourself to be sloppy with these words. And so you're going to have to untrain the sloppiness and then train yourself all over again to be very careful and strict and proper with these usages. Okay. All right, so let's see. The last one, yet another function that will help me understand this line is the parameterization. And we've talked previously about the parameterization. If you have a point on the curve and if you have a vector parallel to the line, and I'm highlighting based on what parts of this parameterization come from what parts of the geometry here. Details for y'all, you can persuade yourself that this point and this difference vector as a direction vector will produce this parameterization. Make sure to fill in those blanks. Okay? But notice that gives me yet a third function here. This function also, in a way, describes this line. And not only is there a calculus of graphs and a calculus of level sets, there is a calculus of parameterizations. In other words, geometric conclusions that you can draw based on the various derivatives of the parameterization itself. That is different from the calculus of level sets, and it's different from the calculus of graphs. So, yet another third function that is useful at some points. And again, if you take this function that parameterizes the line and try to apply the calculus of graphs to understand the line, you're going to get all sorts of nonsense. Doesn't make any sense at all. Okay, so careful. All right. moving along. I've already actually talked through all of this as we've been going through, so I'm not going to repeat all that. Okay, cool fact, very useful in some cases. Every graph is also a level set. This is super handy fact. The nut that makes this all work is this little trivial algebra right here. And again, it's trivial algebra. All I did is subtract the right-hand side over to the left-hand side. Practically nothing happened here, right? But let's make a careful, strictly according to the definitions, careful interpretation of what happened, how I interpret these two pieces of algebra. So first, looking at the top line, this is a graph. We started off looking at a graph of this function f. Okay, now what's on the bottom line here? The bottom line, well, I have equals constant. That means that I'm looking at a level set in the bottom line. So in some sense, we've already kind of done the work. You can see now that what came to us as a graph, we are now interpreting as a level set. So therefore, every graph is a level set. Now, where you have to be super careful about this is in realizing that they're not the same functions. So the function whose graph we were looking at is called f. The resulting function for which I have one of the level sets is not f. Look at this function right here. This thing, y minus f of x1 through xn, this is not f. This equation here, I am not taking a level set of f. Right? Different function. It's got a different formula. It depends on y. Y is one of the input variables here. Right? It has more inputs. The original function f only has n input variables, x1 through xn. This function here has n plus 1 input variables. It's got the same n input variables, but y is also an input variable for this new function.
Would you only set that equal to 0, or can it
I'm not setting it equal to 0. It's what resulted when I did the algebra necessary to have a 0 on the right-hand side. Okay. Does that make sense?
Sure.
Yeah. So setting equal to 0 is kind of an arbitrary choice that is made sometimes. So I didn't find this and then decide it should be 0. I found this in the process of the 0 came before the function in some sense. Does that make sense?
But now that it's a level set, can I put other constants on it?
Well, okay. Now, so you're not using the words quite right there. So this is not a level set. This is a function.
Okay.
This equation where I say g equals 0, that's a level set. Now, if you were to write down a different equation that says, g equals 7, that's a completely different thing. That's got nothing to do with this original thing up here, right? Does that make sense? Yeah. Everybody else okay? Yeah.
So just to clarify, a graph is when y equals a function, and then a level set is when a function equals a constant.
Really close.
Okay.
So it doesn't have to be y.
Okay.
Yeah, but so a graph is when you take a function and you set it equal to I'm going to call a new variable, namely not one of the input variables. And in this case, I happen to choose y, but it doesn't have to be. Yeah. So let me play it back to you, kind of as I think. So taking a graph of a function means setting the function equal to a new variable. Taking a level set of a function means setting the function equal to a constant instead of a new variable. Yeah. Okay. All right. So how is this useful to us? And I'm going to show you just a quick example here. So here's a function. We've seen that function before. And first thing I'm going to do is talk about the graph of that function. Now you see here I've formed the graph because I've set the function f, x squared plus y squared, equal to a new variable. Can't call it x, I can't call it y. Those were the input variables, so I call it z out of just sort of alphabetical sort of convenience and laziness. So that's the graph. Suppose that a question were to come to me that says, hey, I'm interested in the graph of this function, and I want to draw some geometric conclusion about that graph. I could immediately apply the calculus of graphs to the function whose graph I'm looking at. And that's all well and good, but what if that doesn't give me the geometry that I need? What if I look, the calculus of level sets would give me exactly what I want, let's just say. Can I just apply the calculus of level sets to this function? Well, of course not. I'm not looking at a level set of this function, right? What I can do is say, this algebra is equivalent to that algebra. This transformation here, nothing happened here. This is still the exact same equation morally, right? And yet now, the exact surface that I was given, the graph of f that I was initially interested in, now I'm viewing it as being a level set of this other function. So can I use the calculus of level sets? Yeah, sure, to G. Right? I can talk about the calculus of level sets of G because I am looking at a level set of G. Does that make sense? Everybody? So if you want to use the calculus of graphs to understand this surface, then you would apply the calculus of graphs to that function. If you want to use the calculus of level sets, well, you better do it to this function, not f. Yeah.
What is that notation you have there with like the inverse?
Yeah, that's this is just a recognition. This notation right here. Yeah. So remember when what a level set means is that you specify an output value, and the level set is the corresponding input values. So this is the specified output value. And then G inverse says kind of work backwards through the G function. In other words, find the input values corresponding to that. So it's just a convenient notation that says level set. That's all. Yeah. Right. Okay, so neato. And as I started this page with, every graph is a level set. Very cool trick when you have a graph but wish it was a level set. This can make that wish come true. Here's the bad news. It is a one-way deal. While every graph is a level set, not every level set is a graph. So it just doesn't work. And it's easy to produce an example, a counterexample, because here's a level set. There's a level set right there. Level set of x squared plus y squared. Here's what that looks like. It's just a circle. And this is not a graph. Can't be a graph. If it were to be a graph, here's what it would have to look like. I'm going to say graph question mark. It would have to be something like y equals, some function of x. And if y truly were a function of x, that would mean that for every value of x, there would be exactly one. Keep in mind, this is a function, very strict rule. For any input, there's exactly one output. So for any x, there would be exactly one value of y. That's not true here, right? Said differently, this curve fails the vertical line test. So we lose, not a graph. Everybody happy? So one-way street, yeah.
The graphs are only of functions.
You can only talk about the graph of a function. I sure wish we could all agree that would be the usage. It does seem pretty popular for textbook writers to talk about the graph of an equation. It makes me cringe every time I see it. We already have a word. If you have an equation and you want to talk about the set of solutions, it's the set of solutions. or if you don't have that kind of time, it's the solution set, right? We already have a term, but graph means something specific. So it bothers me when I hear people talk about graph of an equation. Does that make sense? Yeah. Yes.
Can you expand a little bit on the notation where you talk about G inverse?
Yeah, that's what she had just asked about. So the idea. Let me just go back to the to that page here. Where's my? Oh, here it is. Right. So the big idea is that for a given output value, let's suppose I specify the output value 2, right? That output value 2, from that we're going to try to find what are the corresponding input values. And so you can see that's kind of working backwards through the function f, and thus f inverse to describe that level set. Is that cool? Yeah. Okay, and I've forgotten who else asked me that, but there's a different point of view there. Yeah. Okay. So moving along, we're going to talk about how to understand equations of 3 variables. Now, there are various different tricks, tools for your toolbox. What there isn't is a single algorithm, hopper that you can toss the question into and turn the crank and out comes an answer. If you have an equation of 3 variables, you've got a problem on your hands, and you've got to think creatively about how you can use the limited tools that you have to understand what that equation represents. So I'm going to start with one of my favorite ones, and that is this statement right here. Very surprising. This is another one of these very small cost to invoke and very big payoff in what you get out of the deal. So here's the cost. You have to look at x's and y's and make sure that they show up only in this form. They show up only as part of that expression, square root of x squared plus y squared. So no extraneous x's by themselves. No e to the x anywhere. No cosine of y plus 7. Nothing like that. X and y appear only as part of that form. Now, this doesn't happen all the time, right? This little trick, this little tool only applies in limited circumstances. But when it does, it's so easy to notice. Just look at where the x's and y's are. And if all the x's and y's are inside of that expression, price paid, and you get for free, as a result, this powerful geometric conclusion. Your surface is rotationally symmetric around the z-axis. And that is a tremendous amount of geometric information that I get for free at a glance. It's a totally awesome theorem. Let me try to persuade you of why this is true. I'm going to give you 2 points of view on this. The most immediate, and it depends on how you look at it, way to do this is to realize that this expression really is distance from the z-axis. It's the cylindrical coordinate r, so it's distance from the z-axis. So, if I were to have a point, and if I were to rotate that point around the z-axis to produce a bunch of other points, such as, for example, this point, those 2 points are totally different points, to be fair. Yeah, absolutely. They have different x's. They have different y's. Definitely different points. But here's the thing. X and y don't really matter. In the equation, x and y only show up as part of that expression. And these 2 points have the same value of square root of x squared plus y squared because they have the same distance from the z-axis because they're rotations of each other. So if they have the same value of square root of x squared plus y squared, and by the way, notice as well, they also have the same value of z, there because, again, you rotate it around the z-axis. That doesn't change the value of z. These two different points will plug into the equations basically identically. So if one works, the other works. If one fails, the other fails. That makes sense to everybody? Okay. All right. Now here's a different point of view you might prefer. Think about what would happen if you converted this equation into cylindrical coordinates. And when you have cylindrical coordinates, of course, everywhere you see an x, you put r cosine theta. Everywhere you see a y, you put r sine theta, blah, blah, blah. But nice shortcut, everywhere you see square root of x squared plus y squared, you get to just put r. Right? I guess technically absolute value of r. But anyway, no thetas. Those are the only ways x's and y's will ever show up. So there's no opportunity for theta to ever show up in the equation. And so, as noted here, there will be no thetas in your cylindrical equation. And I'll remind you from a previous example, it must have been last week at some point, but not long ago, I made the observation that when there's no thetas in your cylindrical equation, that means that all of the theta slices look exactly the same, and that means that it's rotationally symmetric around the z-axis. So, nice alternative point of view. All right. So, who cares? So our surface is rotationally symmetric. So what? Well, if it's rotationally symmetric, again, think about a rotationally symmetric thing. You could just look at any cross-section. Any cross-section tells the whole story because it's rotationally symmetric. That means you could take any vertical cross-section containing the z-axis, that is, any such cross-section. If you just look at that cross-section and rotate the cross-section around the z-axis, you will generate the surface that you're trying to understand. And here's how that can pay off big time. Let's look at this example here. Here's this surface that we already agreed is something that we don't know how to draw yet, quite. Okay, what are we going to do with that thing? Notice, very valuably, x and y appear only in this special form. That means that this is rotationally symmetric around the z-axis. And as I observed moments ago, because it's rotationally symmetric around the z-axis, there's my z-axis, I can pick any plane that I want that contains the z-axis and just look at the cross-section in that plane and then rotate it. So I'm going to pick this plane containing the z-axis. You have a bunch of choices. You could pick the xz plane instead of the yz plane. Whatever. It's all good. Minor observation. Alphabetically, x comes before y, but the yz plane is the one that you're looking right at. The xz plane, you're looking at kind of at an angle, and it's a little bit geometrically distorted, you might say. It's a little bit more confusing to use the xz plane. So when the opportunity presents, all else being equal, we'll go with the yz plane. Okay, so I pick this plane. It has an easy equation to write down, x equals 0. If I want to understand its cross-section, I plug that in and see what comes out. I get z equals y squared. That I already understand. Z equals y squared is a parabola. This cross-section in the plane that I decided to look at is easy. Right, now let's summarize what we have. We know our surface is rotationally symmetric. We know what one of the cross-sections looks like. Then, as promised, I'm just going to rotate that cross-section. And as I rotate this cross-section around the z-axis, I will generate what this surface actually represents. And it makes this kind of bowl shape, like so. Yeah.
So it didn't have to be square root of x squared?
Oh, yeah, that's okay. Great complaint. Okay, let me come back to that in 2 seconds. Does everybody see the connect the dots, the big picture here? Everybody comfortable with the idea that this is this shape? Okay. A little quick lingo first. This is called a paraboloid. It's because it's a rotation of a parabola. Okay, now to your question, she brings up a valid complaint that, wait a minute, I thought it had to be square root of x squared plus y squared. Where's the square root? And I'm going to point out that this is equivalent to a rewrite, which is z equals square root of x squared plus y squared quantity squared. So yeah, even though it's not visible, this perfectly equivalent formulation it is. Yeah, so that kind of thing's perfectly fine. Okay, so a couple more examples. This next one, same basic idea. Interested in this surface. I notice that x and y appear only in the required special form. That instantly tells me it's rotationally symmetric around the z-axis. Pick your favorite plane containing the z-axis. It doesn't matter. Any plane you like. Things work out better if you pick a coordinate plane, but if you want to make life difficult for yourself, you could take like some angled plane through the z-axis. It doesn't matter, right? Just to mix it up here, I'm choosing the xz plane this time. Now, that's being as it is a different plane, it has a different equation. That plane is now y equals 0. That then is what I plug in here to get what my cross section looks like. My cross section is now again a hyperbola. Right, x squared minus z squared equals 1. Let's see here. Now, make sure you're good with hyperbolas. I know that was a long time ago, Algebra 2 or whatever. I don't know, pre-calc, whatever they call it these days. And make sure you keep it straight as to which way the hyperbola goes. And that's confusing. And good luck, but make sure you can get that straight. In this case, this hyperbola looks like this. And now again, reminder, we know that our surface is rotationally symmetric, and we know one of its cross sections. So I can just take this cross section, rotate it around the z-axis, and whatever that makes is my original surface. So my original surface then ends up looking something kind of like this. Like so. Again, because this is a rotation of a familiar curve, this being a rotation of a hyperbola, we call this a hyperboloid. And when we get the next example done, you'll see why we call it a hyperboloid of one sheet. But for the moment, let me leave that dangling. I'll fill in that blank in a minute. Okay, now to get to the next example, I have to go back to where we were originally. When x and y appear only in the special form, the symmetry is around the z-axis. I'm going to appeal to your sense of patterns. That if I were to trade the roles of the variable, there's nothing magic about the alphabet, right? It's not like z is special in the alphabet, right? So instead of x and y appearing in the special form and getting a rotational symmetry around the z-axis, wouldn't it seem like a reasonable guess that if x and z appeared only in the special form, wouldn't you guess you'd get a symmetry around the y-axis? So that's actually true. And it's a nice exercise to think it through. You can totally argue this on your own. The argument's going to look a lot like this here, just obviously with X and Y and Z playing different roles, right? And so, like I say, nice exercise to think it through, and I encourage you to do that. The nice punchline, though, is I can solve questions like this one. So looking at this equation, which, by the way, you will observe conveniently is equivalent to this equation. Notice that Y and Z appear only in the special form. And because Y and Z appear only in the special form, we have a rotational symmetry around the X axis. Is that cool? All good? Okay, so same game. Pick your favorite plane containing your axis. Again, bunch of planes to choose from that contain the x-axis. It doesn't matter, whichever one you like. I'm going to pick the xy plane, no particular reason. And the xy plane has this equation, z equals 0. So taking that, plugging that in to my original equation, produces this output, x squared minus y squared equals 1. That gives me this curve inside of the xy plane. Again, make sure you're good with all your algebra 2 stuff. And so again, same situation. And we have a rotational symmetry. We know what one of the cross sections look like. So I'm going to take this cross section and rotate around my known axis of symmetry, namely the x-axis. And here's where you have to use your geometric imagination. It's hard to draw. I didn't do a great job here. I'd be very interested if anyone can conveniently produce a better picture of this. I think it's really hard to draw. But these curves rotated around the x-axis make it kind of, it's like there's a bowl and another bowl, like a couple of bowls, I guess, about like this. One facing that way and one facing that way. They don't touch, right? But they're sort of close to each other. I also sometimes I feel like this looks like a contact lens, and that looks like a contact lens, and so I call this the staring contest, right? Yeah. Anyway, whatever you think it looks like, that's my best shot at drawing it. So now what are we going to call this? Well, again, it's a rotation of a hyperbola, so hyperboloid. But this time, notice the surface is significantly different. If I can get this thing to, come on. There we go. Significantly different from our first hyperbola. Our first hyperboloid. Our first hyperboloid only has one chunk, and so we say one sheet. Our second one here has two chunks to it, so we say hyperboloid of two sheets. Okay. Okay, so these the next tool that I have for you is what I'm calling deformations. It's just a clever observation about what happens when you tweak an equation a little bit. And let's start with this equation right here. It's an easy one. It's a sphere. You could write down the spherical equation for this. This would just be rho equals 13. Like, no big deal. That's a sphere centered at the origin. Can I use the fact that I know what this looks like to help me understand what this looks like? Now, they're not the same equation. They're importantly different. This blue equation, I can't use spherical coordinates. Right? Spherical coordinates don't work out nicely. I don't know what to do with that in spherical coordinates. So this convenient benefit of spherical coordinates for the green story, I am without that advantage in the blue story. So it would be lovely if there was some way I could kind of use this knowledge over here to help me understand this knowledge over here. The foot in the door is to realize that, of course, they're almost the same equation. The only difference is that everywhere I saw a z, I replaced it with 2z. which makes it a different equation, which makes, points that worked over here not work over here. Easy example, 3, 4, 12, it just works. 3 squared, 4 squared, 12 squared. They add up the way they're supposed to. But over here, if I tried to make it work, 3 squared, 4 squared, and then I have 12 that gets multiplied by 2 to make 24 that gets squared and messes everything up. Okay? So the big idea here is to realize that, okay, 12 got messed up by that 2. Can't I undo that 2? Right? Can't I kind of anticipate having to multiply by 2 and put in a different value of z instead? And so I point out that if you put in z equals 6 instead of z equals 12, that 6 will get multiplied by 2 to make 12, which will get squared and everything works again. Right? So the punchline then is that algebraically speaking, if you replace every z with 2z, algebraically speaking, all of your z coordinates should get cut in half to kind of account for that algebra. Or geometrically speaking, you might say the surface gets squished. It gets kind of compressed in the z direction by a factor of 2 because all of my z coordinates got cut in half and thus the squishing. Right? So this is the big idea. And notice that gives me a very simple answer. Now, in fact, I do know what this surface looks like. Even though I don't have any technique, well, I could make a rotation argument. Right? But let's pretend like I can't do that. Even though I didn't immediately see that I have a foot in the door of, a tool that I can apply here, I can use my knowledge of the green equation and its solution, and I can use my understanding of how tweaking equations geometrically deforms surfaces to kind of, make it work. And so we get to draw a nice conclusion there. Okay, we'll pick up here next time, and see y'all later. Have a good one.
Question for you.
Hang on just a second. Let me get the recording started.